Hi, my name is Michał Dominiak. I work at Nokia Networks in Wrocław in Poland. And I'm here to talk to you about higher order functions. And the title says techniques and applications. There will be more about techniques because I made a presentation about techniques. And it's already too long for the time slot I have. So hopefully I can get through it all. There is microphones that you've probably noticed throughout the week. If you have a question, please use the microphone if you can. If you can't, just shout it. I will repeat it. But it would be preferable if you could use the microphone. And if you have a question during the presentation, feel free to ask it. It's easier. It's very often easier to answer in context. Right. And if there is any standard library implementer here, or a library working group member, I would like to be sorry for misrepresenting your hard work. Okay, we are through with introductions like this. Let's dive in. So what actually is a higher order function? Wikipedia gives us a quite helpful definition, and it says it's a function that has at least one of the following properties. One of them is it takes a function or more functions as arguments, or it returns a function as a result. The second property is slightly less interesting, and there is not so many considerations to be taken, so I won't be really talking much about that. I might mention something somewhere during the presentation about that, but the more interesting part is actually taking a function as an argument, which isn't as straightforward as it might seem. Okay, so, this is not supposed to look like this. I know what happened, and I'm sorry for editing the slides at the last minute. There is just a 0 as the last argument here. That's the thing that I was missing previously, and my editor helpfully formatted it for me. So we have the function in the standard library called accumulate. Accumulate sums all the numbers inside the range that we pass to it by 2 iterators, right? That's the thing it does. Except not really, because really we can use accumulate for anything. A better name for this function would be fold, but C++ has this weird history of renaming things in a way that is not always obvious. But the point is, we can pass anything as the accumulator, like as the function that does the accumulation inside this algorithm. We can pass something like this. So this lambda here indexes the first argument with the second one. So if we have a vector of keys into some recursive data structure, and we have the root element, we can just index all the way down with all the keys. For the purpose of this talk, a function is anything that is callable, just in case I would forget to say this later. This is a function. I'm not going to make a difference between a function object, a lambda expression, a function pointer, whatever, because that's what's interesting for us. Okay, so we can pass a function here. There's another use case which differs in a slight way that is not particularly obvious from the code, but I will mention it later, the difference. Get calculation gives us a future. A future is a representation of a value that will probably arrive in the future. And here I'm using something that's not exactly the .then from the TS, because this .then just gives us a value, not a future. But the point is, I can pass a function that will be executed once the first future is fulfilled. So futures, I don't know how many of you were in Hartmut's talk yesterday, but futures allow us to build chains of dependencies that will allow us to execute code on many threads, on many executors efficiently. All right. We can, of course, merge those two together. This code, I have no clue how this would look like if I couldn't just pass a function inside something else. This would be just crazy. What it does is goes through statements in a function. It's like a part of a compiler. Goes through statements in a function, and once it reaches, the idea is that once it reaches one that always returns, so either a return statement or a throw statement, something like this, it just doesn't do work anymore. Otherwise, it continues and optimizes every other statement. So I don't know how to write this if I couldn't pass functions into other functions. All right. So function pointers are somewhat of a first idea for how to pass functions into other functions. That's how we did it in C, right? So we can have a function pointer type. This one is a template, but it's a comparison function, right? It takes 2 elements and gives us some result. That's Boolean. Okay. And we can have a function like this, which takes 2 elements and takes this comparison and just invokes it, supposedly, and does something if the comparison is true. It doesn't matter what exactly this function does. It's the example I will be using throughout this talk for different techniques. So if we could actually write something like this instead of that pointer there. We can just write a function type and pretend that we are passing functions and not function pointers. Function pointers, it's exactly the same thing. Okay, so if we have a comparison operator, that's a free comparison operator, like here, we can just invoke this function. Right? We pass the function pointer for that comparison operator into this function. By the way, none of the code that's on the slide has been compiled. So if you see a glaring error, please be my compiler and point it out so I can fix it for the slides that will be published after the conference. Okay. However, if our foo defined the comparison operator as a member and we tried to call this function like this, it doesn't work. Because this is a member function pointer and not a function pointer. And member pointers are not pointers, despite the name. We would have to do something like this. So introduce something that can be passed using a function pointer with the correct signature. If somebody decides to declare the operator like this for whatever reason, but if the signature is slightly different, then we also cannot do this. And again, the workaround is exactly the same, but this is not nice, right? We have a function, we want to pass a function, and we have to create another function. This makes no sense. All right. So function pointers are clearly not up to the task that we are giving to them. So let's try something that arrived in C++ 11 and is often considered by some people to be the go-to solution to pass functions around, which I will argue that it is not. Okay, how it looks like. We just get the function type that we had previously, slap standard function around it, and we have our type. And we can write the function the exactly same way. We just change the type def. And now this works. Okay, that's good. This also works. And this also works. So it looks like we achieved our goal. We can pass anything that somebody has declared before into our function. So how does it work? The very short answer is type erasure. The very long answer is on the next 2 slides, which are the part where I'm sorry to standard library implementers for making it seem like they have an easy job. So we have function. Hopefully you can all see this. We have a function. First we have to declare the template. Then we have to do some pattern matching to actually determine the signature that somebody has given us. We are going to do type erasure, and the kind of standard type erasure way, like technique, is to have a base class that exposes some interface, keep a polymorphic pointer to that base class, and then do something funny. But this is our interface, so the only thing that we are allowing here is calling the function, which is not exactly all that's required from standard function. But we have the base pointer, and so our call operator of the function thingy will just use that virtual function to do the dispatch. Then we have the constructor that just creates a proper implementation. What impl is, we will see in a second, and moves the value that was given by value, and everything's fine. And then we have impl, which actually stores the thing that was passed to function, and when invoked through the virtual function call, it calls the proper function using standard invoke, which is the thing that allows us to pass member function pointers, for example, into this. So standard invoke is a C++ 17 feature as a function. It was previously a syntactic macro, which wasn't really macro because it was overloaded, but it was used throughout the standard library. So standard function uses it, standard thread uses it. It allows us to pass any callable, and then some arguments, and invoke figures out how to actually call this thing. Okay, so this is the classic implementation of this. There's a lot of function pointer dereferences here. Pointer dereferences. There's a lot of jumping around. We have indirection through data. We have indirection into the vtable, and then we have indirection into the actual call. Which is not particularly good. So we are going to forget about this implementation, although I think this is what some implementations do. I think I tried to look at libc++ while trying to run here and be on time, and I think it uses something like this. I'm not sure about libc.c++. We are going to work with a slightly different version that allows us to do slightly more things. So it starts the same. But then we are going to have a function pointer inside. So we are going to use some more functions to implement function, which is kind of nice, right? Building functions out of functions. So by default, this pointer is going to be null. This is not actually used anywhere here, but it could. Okay. And then we are going to have this weird-looking type, which is a unique pointer to void with a custom deleter. The deleter is a function pointer. So at any point, we can change what happens when the deleter is called. So those two members are the part that powers our type erasure in this implementation. Invoke erases the actual code that needs to be called to invoke the function, and data erases the actual type of storage for this function. Does this make sense? I hope it does. Okay. Then our call operator will just grab the void pointer, pass it into invoke, together with all the arguments that were passed into this call operator. And now the building block that makes sense actually is the constructor. There's some crazy code going on here, but it's not that crazy once you look at it closely. The data just makes a copy of actually it moves the thing that was passed as an argument, and then sets up the deleter to actually invoke the correct destructor. And the first one, the invoke, just saves a function pointer to a function which knows which type is stored in data, so it can do the proper reinterpret cast and actually invoke this thing. Hopefully this makes at least some sense. If not, please look at the slides afterwards. Hopefully it will start making sense. Okay. Yes? Can you use the microphone?
Shouldn't you call the destructor directly instead of delete? Because that was not the stack allocated.
Come again? Can you ask it again?
Shouldn't you call in the custom deleter, the destructor itself as opposed to delete because the object was not heap.
I'm doing new. Notice that the first argument into data is a nude pointer. So I'm deleting that thing. Right? Make sense? Yes? How is this faster than virtual call? Less pointer indirections. So a virtual call has to look through the unique pointer that we have to find the v pointer that points to the v table where it finds the function that it wants to call. This has the function that it wants to call immediately here. It's called invoke. So it's one indirection. I have, yes, kind of. One less indirection, yes. But in a tight loop, it's going to add up, right? But this is nicer for other reasons too, so stay tuned. Okay. Does this make sense to everybody? Is there any, yeah?
When I tried doing this technique on Visual Studio, it wouldn't work if I used the member initializer list. Is that why you don't do it either in that slide?
In Visual Studio, it wouldn't work with a member initializer. I'm not doing this here with a member initializer because I think this looks nicer, and the member initializer in this case looks like crazily. I have no idea whether it would work in Visual Studio or not. As I said, this is not actually code that I've compiled, so I deeply hope that I haven't made like a stupid mistake.
All right.
All right, so we are going to go forward because, as I said, this is slightly longer than this time slot, so we'll try to get everything that we can. So there are some problems with standard functions. First of all, it requires that the thing that we hide behind it is copyable. Because the type erasure thingy actually also has a clone function or something like this, because function has a copy constructor, so everything that we pass into it has to be copyable, which is not optimal. I keep playing with this. So we cannot actually hide move-only types behind a standard function. So my opinion here is that standard function shouldn't be copyable, and we should have something else called something else that actually is copyable. This ship has unfortunately sailed. And I have the paper mentioned later. All right. There's actually a paper that helps with this. Another problem. Imagine we have this thing. It has a non-const call operator which just which increments the value it holds and returns it, and we have the const one. Right? The const one doesn't change anything because it's const. So if we just create a some function object instance and call it like this, we will get 1. If we create an instance like this, we will get 0. Right? That follows from the code. Now we wrap them. So the first one, when we wrap it in standard function, the assertion won't fire. If we wrap the second one in standard function, we have a problem. Because it is going to be the non-const call operator that is going to be called here. Why? Well, remember this thing? This operator is const. So it can be called on a const function. And data itself isn't const. It's just a void pointer. We are not trying to propagate the constness here, which is kind of unfortunate because it leads to surprising behavior like the thing above. So I would like to be able to write this and have the proper behavior and have the previous slide not compile at all. There's a paper for this. This is some slides here are like there's a paper about this. From David Krause, P0045. Do you remember the exact status, Matt? Okay, it's going to have another revision. Okay. So this might be actually coming. So this would be nice. The paper actually also deprecates the const call operator. So the code would still compile, we would have a migration path, and then at some point it would be removed. So that's a nice way to get rid of this problem. How we are doing with time. Okay. So when we are doing type erasure, and notice that this slide doesn't say problem with standard function, it says problems with erased wrappers. So this is going to be a problem whichever approach we take with type erasure. We cannot actually deduce any part of the call signature. We have to know the call signature for this to actually make sense. So with argument types, this is not really hard because generally we know with what arguments we want to call a given function, right? But with return types, it can be hard, and there is a lot of questions on the internet. How do I do this? The answer is usually you don't. So we have a function like this, with the return type being a template parameter. And we have a function like this. We cannot do this. Because the compiler doesn't know what the template parameter is, because it's not able to deduce it here. So we could do some silly thing like this, as it's a function. So the decal type will actually give us the correct function type. This is ugly, right? What? I cannot understand you. I mean bar as an argument. Yes, thank you. Yes, the last line should say foo of stud function decal type bar address of bar. Thank you. So we can actually spell it, but spelling it is like contradicts the idea of type deduction, right? So we cannot actually do anything useful with this. The code gets very, very, very verbose very quickly. Okay, that's it for now about standard function. Another way to pass functions into other functions is actually pretty widespread in the standard library. The standard algorithms pretty much all take their arguments this way. So instead of having an alias, this time we are just going to have another template parameter. This gives us some flexibility because with erased wrappers, we are kind of locked into having either value or reference wrappers. Kind of, because it's not really true, but it looks so. Here we can specify anything. So we can say comparator ref, and it will work. So assuming the person implementing do if true knows what he's doing, so namely he uses invoke, all the things we tried before will work. So this will work, this will also work, provided invoke is used. This will work either way. So how it works, you probably know how it works. It generates a new function for every different thing that's passed into this function. So this case, we can actually do some more deduction. So as we are deducing the argument type and not the call signature itself, we can knowing the arguments, we can find out what the return type is. So, for example, we can write something similar to this. It's very much like the deduction we tried with standard function, only this time we have 3 arguments, not 2. Okay? Actually, this should also say standard invoke, but whatever. This is templates, so you could also do some funky stuff to try to deduce the arguments themselves, but let's not go into that. You can, in some cases, but let's forget about it for now. So deduction isn't always your friend. So say we have a function like this, and we have an overload set like this. We cannot call foo with an address of bar, because the compiler doesn't know which bar we want. If foo specified what function pointer type it wanted, this would have worked. Because function pointer, like conversions, not conversions, like taking an address of a function is the only place in the language when information flows backwards. So context of the expression actually changes what the expression means. So we can write something like this, which will give us the first overload of bar, but this is not very nice, right? We are back to we cannot deduce anything. We can write this. How many of you like this abomination that's on the slide right now? No hands, good. There's been a proposal a while back with some revisions that would say the thing on the bottom is equivalent to the thing above it. So just passing overload sets as objects. It's basically a way to generate the lambda above. As I said, that proposal had revisions, but the authors of the recent revisions are not very eager to actually pick them up and go back to the committee. I plan to do this in some time, but I don't know which meeting that will be for. Maybe the next one, but I don't think I can make it. But this would be nice, right? All right, so code bloat is often an argument against templates, right? And we are generating a new function for everything that we pass into some other function. This allows the compiler to do more, because the compiler knows exactly what's going on. It can inline more aggressively, optimize more aggressively. This is why standard sort will often outperform like qsort from C. But we pay for this by making the binary bigger. Often, this does not matter at all. But there are some environments where this is going to be a problem if you use this technique extensively. And actually, this little guy on the bottom here, while we are at compiler optimizations, carries more information than a function pointer. This lambda can be expanded into just a call and can be inlined. If we pass a function pointer, then unless the compiler does some devirtualization weird things, then it's not going to be able to actually inline the function. All right. So with template arguments, generally we only get static polymorphism. which works only at compile time. And if you need runtime polymorphism with this technique, you are going to have to wrap them in a function, like a standard function. But then we are kind of losing the deduction is your friend part, because suddenly we have to spell everything out, because the compiler is not going to figure out what is the call signature of the thing that we are hiding behind the standard function. But this should not be a surprise to anybody using templates, right? Now, if we wanted to constrain the signature, this is also not going to be pretty. So we have this function, still the same, and we have some foo, which does nothing, takes no arguments. Clearly, our intention is that do if true should not be callable with foo as an argument. Clearly, right? And if we just call this function like this, then the place where we will get a compiler error is inside do if true, which makes it not detectable at compile time, which means that nobody can spin on whether he can call our function or not. So what we will do, first we need to make some space, and then we are going to put some crazy template things inside. I hope this is correct, because I copy-pasted it from somewhere else. So we are checking whether we can convert the return type of this function to the one we expect. Actually, R should be bool. Yeah, sorry for that. As I said, copy-pasted from somewhere else. Because I want to never have to write code like this. Like, I like writing templates. This is not the kind of templates I want to write. So this is crazy, right? Concepts help a little bit. We'll see how much they help in practice. But they certainly make this code slightly more manageable. All right. So at this point, we are past the standard territory, and we are somewhere else that might sometime be acquired by the standard. Function ref. The name suggests it's a function and also a reference. And that is the point. We want to pass something that's callable as a reference, while also keeping the information about the signature and so on available. So it looks pretty much the same as function. So we just replace the name, everything's all right. And again, we can call this function like this. This also works. This also works. Great. So what's actually the point and how it's implemented? So the answer to the second question is type erasure again, because how else are we going to do this? And we are actually going to go with the second implementation of function and kind of morph it into a definition of function ref. So the first thing we need to change is the name, obviously. We had the invoke function pointer, which did the hard work for us. This is going to stay the same. We had the unique pointer to void with some deleter. This is the part that's going to change. We don't actually need a unique pointer. We all can deal with just a void pointer. We had the call operator. Well, it used the data pointer. It used to be a unique pointer. Now it's just a raw pointer, so we can just remove the .get. That's nice. Then we have the constructor, which used to look like this in function. And of course, I didn't change the class name of the name of the constructor. So there is actually two differences. One of them is how we initialize data, and the other one is how we take the argument. So in function, we just grabbed the value, right? In function ref, we are going to take a reference, because that's what we want. We want a reference to a thing that actually exists already. And then instead of using new to initialize a unique pointer to hold our data, we just save a pointer to the data somebody passed to us. Just grab the address. And everything else is exactly the same. So function ref is a reference. References have this problem of lifetimes. When we pass something by reference, it's take my word that this thing is going to be alive for as long as you need it. This is what a reference means. It's easy to pass a temporary object. That was kind of intentional due to the next slide. But it makes it easy to write slightly incorrect code in some cases. We will come back to this. So when you have function ref, you have to either not save it or tell the user, hey, you better remember that the lifetime of the reference you are giving to me is going to be longer than you might expect from just looking at the code. And otherwise, we get dangling references, which is just a bad thing. And especially if you ever had to debug like code that heavily used futures, and somebody made a mistake of capturing a thing by a reference instead of by value, debugging that stuff is going to be pain. I've done it. I've made mistakes like this. I know the pain. So my opinion here is that we actually need core language lifetimes. I think that we need a core language feature that tells us what the lifetime of this thing is. Library features, I don't think cut it. I think it's the compiler that must actually do the checks whether we are doing something illegal. This would, of course, be optional, right? But I think we need this thing stuff. But please, please, please make it look slightly better and in general, be more manageable than in Rust. Because Rust lifetimes, I don't know how many of you had the pleasure of working with them, are not very great. Yes? Is there a way to prevent R-value references from construction? Yes, but I actually don't want to do that for reasons that I have on slides later on. Somebody want to disagree with my comment about Rust lifetimes? Good. Okay. So, function forces reference semantics. This is the same problem as on the previous slide, just it's the flip side of it. And this means that it's not very easy to pass a copy of the value that we have. If we explicitly don't want to pass the object we have as a copy, we know that in a given case it's safe and we want to pass a value. There is no easy syntax to do this. And this is why I support R-value references there. So I have a function ref, and I have some callable, and I want to pass a copy. This passes a reference. This will pass a copy, but at the price of having a separate statement, right? That statement might be like completely disconnected from the code that uses it in some cases. What I would ideally like to be able to write is something like this. Look at the comment. We can already do this in one context. You can say new auto, and with a single argument, this expression will deduce the type It has to allocate and initialize and give you a pointer to. But we only have it there, as if new was something that we were using frequently and needed this feature for. I think this is a place where we more need this type of deduction than anywhere else. Do I know if there's a rationale for why we can't write this? I had a discussion with Ville at some point about this, but I don't remember if there was rationale. I think it was like nobody thought of it. Yes?
You can maybe have a free function copy. And
Can you close it?
you can have a free function copy.
Yes, I can have a free function copy, but that free function copy is going to be a template. That template is going to be instantiated every time I call it for different arguments. And as one of our friends who is here at the conference, I don't know if in the room, is going to teach us in some of his presentations, creating an instance of a function is one of the most costly things to do at compile time. Of course you can do this. Whether you should depends on how long your compile times are right now. All right, so this is the part of the presentation where there is a lot of text on the slides, but not really much code. So brace for it. There is a bunch of my opinions that I know some people don't share. I propose that whether we care about ownership depends on the kind of a function that we are working with. This is what I was talking about previously. And this goes back to the first section, to the example with like accumulate with .dense inside. We have two different kinds of functions that we pass other functions into, generally speaking. We have synchronous functions, which are going to fully execute below our context. And they don't save anything that we pass to them, so we can pass references. We can pass references to temporaries, and nothing is broken, which is why I also want to support error value references for function ref. And there is asynchronous functions, which are probably going to save the callback we gave them. So for synchronous algorithms, whether we have value semantics or reference semantics doesn't matter, because the lifetimes are not going to be a problem. For asynchronous functions, reference semantics can lead to illegal behavior. That means dangling references. Can. But will not necessarily lead to the undefined behavior. If we can guarantee that the thing that we are passing via reference will be alive for the entirety of time it needs to be alive for, everything is fine. We can pass by reference. It's cheaper. We allocate less memory. We don't have to copy stuff around, and so on and so forth. So for synchronous algorithms, we will generally want to benefit from the performance of function ref, right? There is no reason not to. For asynchronous algorithms, we, as the caller, would like to be able to specify whether the thing that we are working with is going to outlive the asynchronous context or not. The author of the API doesn't know. He doesn't know what we are passing into his function. We know how long the object we are passing in is going to live. So it would be better if we could make the decision. So I propose that the decision of value versus reference semantics should not be tied to the algorithm itself. It should be tied to the way the algorithm is invoked. That is my ideal way to write code that takes functions and other contexts too. But we are mostly talking about functions right now, so let's stay there. Although, of course, an algorithm should be hard to use incorrectly. So the default should be the safe behavior. We should have to explicitly say we want the thing that is potentially unsafe. This is general guideline, right? However, if we have two behaviors that are correct, so neither of the semantics will cause bugs, and we can guarantee that. This sentence might look and sound complicated, but I think that the default should be the one that is harder to use when it is not a default. In other words, the behavior we have to opt into should be the one that is easier to opt into. So opt-in pass by value, that is, pass me a copy into this thing, and by default pass a reference, is harder, right? We saw that. It would be not much harder if we actually had the auto thing, or if we can pay for copy function that's instantiated for everything. But generally speaking, you have to spell the name or use decal type to construct the thing, or use a macro. Oh no. Although, when we can pass by value, we can very easily pass by reference too. There is this little thing that everybody hates that's called standard reference wrapper. How many of you like standard reference wrapper? Can you half raise your hand? Yes, you can half raise your hand. All right. So standard reference wrapper is a weird thing. It's a reference, but it's not a reference. It looks something like this. So we have a constructor. We can construct it from an L value. We cannot construct it from an R value. Which kind of, again, goes back to your question, right? We can get a reference. It's convertible to a reference to T. And it also has this one little curious operator down there, which is only present when you can actually call it. So it's finite away. It's a call operator. I actually didn't know that existed in the reference wrapper like a couple of days ago. Matt told me that it exists. I was like, wow. So the way to create a reference wrapper is call a function called standard ref, which is easy. It's short. So this code compiles and works the way it should. But there is a kind of big thing going on here. Standard function is a pass by value thing. Except it's not. Because we can create types that look like values, but behave like references. So I have one problem with this. Namely, it's still a standard function. It's still going to be as expensive as standard function. We have to copy the reference wrapper. We have to allocate memory for it. We have to store it. What if we could do something different? So this is function. This is not function ref. We go all the way back to function. This time I call it my function because it's how I would like to have it. There's one thing missing. Then that one thing missing is a constructor from a reference wrapper. So when we construct from a reference wrapper, we can, again, save the address, just like in function ref, and we can set the deleter to do nothing. So if we are given a value, we allocate memory for that value, we save a way to deallocate the memory and free the resource. If we are given a reference wrapper, which is a value meaning a reference, we just save the address and don't free anything in our destructor. And invoke is exactly the same, because it's the same thing. Makes sense to everybody? So we've saved, again, like a pointer in the direction. Because reference wrapper, what it actually is, it's a pointer. So if we allocated a new reference wrapper and went through that, we would have to go for another pointer to get to the thing that we want. In this case, we just saved the pointer and saved ourselves a pointer of the reference and saves ourselves a memory allocation. At the cost of like a function pointer over a function ref in space requirements, because the unique pointer here is going to store a function pointer. So that's the one thing more that we have over a function ref. So if I use my function instead of function ref, I lose some information. If the user is meant to pass me the same thing, I lose the information of this is a reference. This is kind of dangerous, but as long as we document exactly what we do, and we assume that our user is not an idiot, then everything should be fine. I know it's a big assumption. Yes, I know. But if we use my function instead of standard function, we don't lose any information, because standard function can already hold a reference wrapper, only slightly less efficiently than we do here. So, not a big deal. So it can lead to more subtle bugs. So we can more subtly point to data that we shouldn't be pointing to. But the thing is, now that we don't pass anything by reference implicitly, we always have to say studref. Suddenly, the caller side that uses our API explicitly says, I'm passing a reference. So while it can lead to more subtle bugs, especially if we throw the function thing around and we don't exactly know where it came from, we can have a problem. But on the caller side, tracking bugs like this should be kind of easier, because we see, oh, I'm passing by a reference. What am I thinking? So this is like kind of a double-edged sword. We can cut ourselves, we can kill our enemy. We have to be careful, but every time we use references, we have to be careful, right? Every time. That's why I like how this works. Yeah, and this problem we already have with standard functions, since we already can pass studref. Okay, so one last unique point is that my function doesn't actually require copyability, because I don't have a copy constructor. I don't need that. This is what I want in many places, like when I'm implementing a future, which is a dear and close topic to me. I don't want a copyable thing, because sometimes somebody will give me a lambda that captured a thing that's not copyable by itself. I don't want to have to invent a new type to deal with this. I mean, I kind of already have it on my slides, right? But I want the standard to have it too. And there's nothing in the standard currently that does this. But there's a paper, P0288, right? Yeah. A polymorphic wrapper for callable objects, which proposes a unique function which is exactly this. It's, again, by David Krauss. All right, we are going to the end. And somehow I made it on time. All right. So some takeaways. Some of them were spelled before, some of them I'm spelling right now. When you have static polymorphism, you can implement dynamic polymorphism on top of it, but not the other way around. Some people forget about this. Slap dynamic polymorphism everywhere without thinking. Sometimes it's better to have like static polymorphism by default, and then for some cases use some hierarchy or a value semantics wrapper for polymorphic things as the fallback. We can mix polymorphism types, especially now that we have variant. If you don't require runtime type erasure, don't use type erasure. Just use template arguments. Function ref is nice when we want just to say, this is only a reference. It might be in your best interest if you don't store me. It's completely fine for those cases. Stud function looks like it says this is a value, but that's a lie. Even if reference wrapper didn't exist, like implementing reference wrapper is 5 minutes of writing code. And that's mostly Sphinx for the call operator. The thing that I did with the unique pointer and sometimes making the deleter do nothing is what I like to call ownership erasure, because we are not only erasing the type, we are also erasing who is actually the owner of the data. And it gives you the same semantics. If you are already supporting reference wrapper, which standard function implicitly is, then this might be a nice thing to do, to reduce the number of allocations you do, to reduce the number of pointer redirections you do, and so on. It's way more scary in some other cases. So if you are implementing like a generic value semantics wrapper over a polymorphic thingy, this is way more scary. But I still intend to use this in some cases where I kind of have a variant of a raw pointer and a unique pointer. This is exactly this. Standard functions requires too much. And I hope that unique function lands quite quickly because I have many use cases for it. And there are some links. You probably can't copy them quickly enough. They are going to be in the slides that will be in the GitHub repo. The first two are the standards proposals. P0045 is again a qualified call signature thing for standard function. P0288 is the unique function paper. The third link is Vittorio Romero's blog post, where he does a quick thing with implementing function ref, calling it function view, and does some benchmarks comparing how it fares against standard function. And the last one is a draft of a proposal for function ref, also from Vittorio, this time with the proper name that doesn't look like it's a range. So expect this to be coming soon to a standards committee near you. And that's all I have for you. If there's any questions, come on to the microphones and ask them. Thank you.
I think that std function uses this small buffer optimization, so there won't be any memory allocations when you use it with the reference wrapper.
Stud function uses small buffer allocations. It probably does in some implementations, yes. But you are still going to pay for the pointer indirection. It's going to be in the same cache line, so it's not going to be as bad, but it's still going through all that. Yes.
Hi, thank you so much for the talk. I did something similar in my company, and I had a question. What was the idea behind not copying? Like I used a basically similar implementation, but a shared pointer only when you had like an R value, like anonymous lambda type. So you would store that in a shared pointer, which could be copied. Otherwise, you just had the invoker for the member function pointer or non-member function pointer. I was just kind of wondering what was the idea there. Was it just a performance issue? And
can you reformulate the question?
Basically, what was the idea behind not copying and using a unique pointer versus, say, like a shared pointer where you could copy the object across?
Oh, so shared pointer doesn't actually implement your copy semantics. It makes your function be a reference to its internal data, which is
right.
It depends on your use case, right? Sometimes that's going to be what you want. Sometimes you will want function to be like a shallow handle to some data sitting somewhere. But that's not what I usually want, which is why I'm using just unique pointer here.
Got it. Thank you.
Have you actually done any benchmarking?
Can you? Yeah.
Yeah. Have you actually benchmarked the speed of this technique with my function versus what standard function does with virtuals and the small buffer optimization? I mean, you're claiming it can be faster because
Vittorio has benchmarks for function ref versus function pointers versus stud function, and this is pretty similar, right? My function is a function ref when you pass a reference wrapper, and is a stud function when you pass a value.
Okay.
Right. If that's all, then thank you very much.